Here we talk about the physical properties of group 13 elements. These elements are boron, aluminium, gallium, indium, and thallium. The first property that we discuss is the atomic size. For atomic size, there are two criteria we discuss. That is, first is along the period or across the period, and the second is down the group. First, about across the period, as we move from left to right in the periodic table, if we see the rough work, like the rough outline of the periodic table, it is something like this, right? These are S block elements, these are P block elements, and these center ones are D block elements. This is F block elements. These include lanthanoids and all. We are not discussing that. Talking about the D block elements here. Sorry, the P block elements here. As we move from left to right across the period, the size will decrease. Why does the size decrease? As we move across the period, electrons are added to the same shell. Electrons are added to the same shell, like this. Right? Thus, the effective nuclear charge experienced by these electrons, it increases because electrons in the same shell do not screen each other. It means they do not protect each other from the nuclear charge of the positively charged nucleus, which tends to attract these electrons. This results in increase in the effective nuclear charge. Effective nuclear charge is represented by Z effective. Therefore, the size decreases as we move across the period. Talking about down the group now. Down the group shows an interesting trend. Here, why is it? So, boron, aluminium, gallium, indium, and thallium. As we move down the group, the size is expected to increase, right? Because new shells are added up. Therefore, size should increase down the group. But here, size of gallium is seen to be smaller than that of aluminium. ज़्यादा होना चाहिए, but it is smaller than that of aluminium. Why is this? On moving from aluminium to gallium, there are 10 transition elements in between. Transition elements, these are D block elements. There are 10 D block elements in between. This results in the presence of inner D orbital electrons in gallium. Therefore, the electronic configuration of gallium becomes 3d10 4s2 4p1. These d electrons, they have very poor penetration power. Therefore, they are not able to shield the electrons. Therefore, they do not shield the electrons, as a result of which the electrons of the s and the p orbital, they experience slightly higher effective nuclear charge of the nucleus. Therefore gallium का size decreases. This is for gallium, right? Okay. Now, the closer an electron can get to the nucleus is referred to as its penetration power. The closer an electron can get is referred to as its penetration power, which is very poor for d orbital electrons. Therefore, they do not shield these outer ये बाहर वाले electrons को protect properly नहीं कर पाते. Therefore, these outer electrons experience the pull of the nucleus and are pulled towards it. Therefore, the size will decrease for gallium. Right? So this is the overall trend for atomic size. The atomic size then continually increases for indium and thallium. It decreases as we move from aluminium to gallium. The second property which we talk about is the melting point. Melting point, it depends upon the packaging of the atoms, the type of packaging present inside the atoms. Now, the melting point, it shows an irregular trend. From gallium to aluminium, it decreases. It to gallium also it decreases, but from gallium to indium and from indium to thallium, melting point is seen to increase. There is an irregular trend across down the group. There is an irregular trend down the group. Now, why is that? Boron has a high melting point because boron is a non-metal. It is stable and is held by strong covalent bonds. It is held by strong covalent bond which becomes difficult to break them. They can be broken but with difficulty. Therefore, it has a high melting point. This melting point is around 2453 Kelvin. Right? Then for the rest of the elements are metals. Aluminium is a metal. Transition from a non-metal to a metal. It has a metallic lattice. Comparatively weaker bonds are present, therefore the melting point will decrease. Weaker bonds, therefore melting point decreases. Same goes for gallium. Again, weak bond, melting point decreases. For indium and thallium, their size, here we see is, for indium and thallium, they have comparatively closely packed structure. Therefore, their packing efficiency increases. For indium and gallium, their packing efficiency increases. Okay, this is indium and thallium. For indium and thallium, the packing efficiency increases. Therefore, their melting point also increases. The important irregularity is between that from boron to aluminium to gallium. And then indium and thallium, they have comparatively higher melting point. The third physical property that we discuss is the ionization energy. Boron family, they have outer electronic configuration as ns2 np1, right? Now, the first ionization energy is very less. Since there is only one electron in the outermost p orbital, it is easy to remove this electron. Therefore, first ionization energy is very small for boron family. Also, if we compare the ionization energies of first ionization energies of alkaline earth metals, ns2, they have outer electronic configuration which is a fully filled electronic configuration, as compared to that of first ionization energy of boron family. Alkaline metals have larger ionization energy than that of group 13 elements. Why is that? Since in group 13 elements there is an outer electronic configuration of np1 and one electron is easier to remove as compared to the fully filled electron shell in alkaline earth metals. Now, talking about the second ionization energy of boron family of group 13 elements, after removal of np1, stable noble gas configuration is reached. Therefore, it becomes difficult to extract electron, and their second ionization energy is higher now, right? Same goes for third ionization energy, that has a comparatively half filled orbital which is also stable, and it is difficult to remove this electron, therefore more energy is required. This was the comparison for across the period. And now we talk about as we move down the group. As we move down the group for ionization energies from boron, aluminium, gallium, indium to thallium, boron has the highest ionization energy, right? Boron is the smallest in the group. Then aluminium ka size is greater than that of boron, therefore it has a smaller ionization energy as compared to boron. But here is an exception. There is a sharp decrease of ionization energy from boron to aluminium. But in case of gallium, in gallium same inner d electrons are present. These inner d electrons, their shielding power is very less effective as compared to those of n and p orbital. They have a poor shielding. Therefore, outer electrons, p and s orbital electrons, they are held tightly. These are held tightly by the nucleus. Therefore, to remove the electrons from gallium is comparatively difficult. Therefore, its ionization energy increases. Generally, down the group, ionization energy is supposed to decrease, But moving from aluminium to gallium, ionization energy increases due to the presence of inner d electrons, which have a very poor shielding effect. Then moving from gallium to indium, ionization energy decreases. But similarly, as we move from indium to thallium, there is a presence of inner d electrons, poor shielding effect. Therefore, the ionization energy increases slightly. Talking about the fourth physical property is oxidation state. Oxidation states. Now these elements, their outer electronic configuration is ns2, np1. Their outermost electrons have outermost orbitals, they have 3 electrons. Therefore, these elements can show a maximum of +3 oxidation state. That is, they can remove these 3 electrons by using higher or lower energies. Then these elements also tend to show +1 oxidation state, which becomes more stable as we move down the group. Right? As we move down the group, here from boron, aluminium, gallium, indium to thallium, as you are moving down the group from +3, +1 oxidation state becomes more stable, right? This is due to an effect called inert pair effect. Inert pair effect is defined as the reluctance of S and p orbital electrons to take part in bonding or to participate in bonding. That is, S and p electrons, they do not participate in the bonding. Therefore, after the removal of first electron in thallium, after the removal of this first p orbital electron, a stable noble gas configuration is achieved. The electrons thus do not participate in bonding anymore. Therefore, they only show +1 oxidation state. Right? Here the definition says inert pair effect is defined as the reluctance of only s orbital electrons to not take part in bonding. Reluctance of s orbital electrons to take part in bonding is called inert pair effect. These s orbital electrons, they achieve a noble gas configuration once the first electron from the p orbital is removed. Therefore, thallium shows a stable +1 oxidation state. Thus, Thales compounds which shows +1 oxidation state, they are seen to be more stable as compared to thallic compounds. Thallic +3 oxidation state. IC word is used for the compounds which show the highest oxidation state. Here it's +3, and OUS word is used for the compounds which shows the smaller oxidation state. Therefore, Thales compounds in case of thallium are more stable as compared to thallic compounds due to inert pair effect. Right? The fourth property is electropositive character. As we move down the group, boron is a non-metal. Rest of these elements, these are metals. Moving down the group, electropositive character increases because ionization energy somehow decreases, right? Now, third is tendency. Next property is tendency to form covalent bonds. Tendency to form covalent bonds. Boron, the first element of this group, is very small in size. If we compare it to rest of the elements of the group, it's very small, and it shows a +3 oxidation state. If it removes these 3 electrons, then it becomes even smaller, a teeny tiny boron particle. Therefore, it is a very small cation. Smaller cations tend to show higher polarizing effect on larger cations. Therefore, it has a high polarizing power. Polarizing power is the ability of the cation to distort the electron cloud of an anion. Due to its small size, boron shows high polarizing power. Polarizing power is the ability to distort the electron cloud of anions, of larger anions. It shows higher polarizing power, therefore it will pull their electrons towards it. Therefore, it will pull their electrons towards it. If we take an example of BF3, in BF3, fluorine is a negative anion. So, boron will form bonds with this BF3. It will attract the negative electrons, it will pull the negative electrons towards itself due to its high polarizing power, which is because of the small size of the boron element. Therefore, it shows covalent character. Then the other elements, they show ionic. As we move down the group, other elements including gallium, aluminium, indium, thallium, they show ionic as well as covalent character.